Okay, so welcome to the problem solving session for the randomized algorithms course. So we had a session yesterday on Friday, but I forgot to record it. So I'm recording it today on Saturday morning. So yesterday we solved the four problems. Today we'll go over the solutions of those four problems again. And if we have time, we'll solve one more problem. Okay. So the first problem we looked was from week one. The problem is the following. We are given an array ARR 1 to n, so the length of the array is n, and we also have the guarantee that either at least 60% of the elements in the array are A for some fixed value A, or at most 40% of the elements in the array are A. And what we want to do is we want to come up with a deterministic algorithm as well as a randomized algorithm which can differentiate between these two cases. And we want to know what's the running time for the best deterministic algorithm and what's the running time for the best randomized algorithm. Okay. So first, let's look at a deterministic algorithm. A deterministic algorithm is fairly trivial. All you do is go over the entire array and look at every element and see if it's A or not and maintain a count. Okay. So just count the frequency of A. So the deterministic algorithm is the following. Yeah, so this is the deterministic algorithm. And so the running time of this is order n because we are going over the entire array. And it turns out that if you want to use a deterministic algorithm, you can't do much better than order n because you will have to go over at least the first 40% of the array, or let's say 40% plus one element to decide whether the array has at least 60% of A's or not, right? In the best case, what would happen is that you would encounter the first 40% plus one elements, and you would see that these are not A's. And so you can say that, okay, there can't be more than 60% of the A's. But you'll have to go over at least 0.4 times n many elements of the array. And so for a deterministic algorithm, you cannot do better than order n. It turns out that for randomized algorithms, you can do something much better. In fact, we will show that you can uh, use as few as like order root and log n many. You can look at most order root and log n many elements in the array and still be reasonably sure that it has either at least 60% or at most 40% So let me give the randomized algorithm. So here m is a parameter we'll fix later in the analysis. So we pick A uniformly. Okay, A is that element. So let me say B. Oh, I forgot to count. Ah. Yeah. So this is the randomized algorithm. And the running time of this is order m because we are the loop runs for order m time. And additionally, n log n because to pick an element uniformly at random from ARR 1 to n, we need to pick an index uniformly at random from 1 to n, and this takes order log n time. So running time is okay. So now what we'll do is we'll analyze the success probability of this algorithm using concentration inequalities. So we have seen three concentration inequalities: Markov's inequality, Chebyshev's inequality, and Chernoff mount. We'll analyze using all three inequalities and compare the results. Okay. So there are okay. So we want what do we want to do? We want to upper bound the failure probability of the algorithm. The algorithm fails in two cases. The first is when the array has at least 60% of the A's, but algorithm outputs that at most 40% of elements are A, and the other is when the array has at most 40% A's, but the algorithm ends up outputting greater than equal to 60% of the elements are A. I will analyze only one of these cases. The analysis for the other case is analogous. Okay. So the case we'll analyze is this. Okay, so let's define some random variables. Let me call this Pi, the B of the ith iteration. Okay, so now notice that algo outputs then only if x is greater than equals to 0.6 times m. Okay, so we have a random variable which must be at least 0.6 times m, and we want to upper bound the probability of this happening, right? So we can use Markov's, Chebyshev's, or Chernoff for Markov's and Chebyshev. Uh, okay, for all three of them, we require the mean of x, but for Chebyshev required, we also require the variance. So let's find these out. So expected value of x is by linearity of expectation, the sum of expected value of xi, which is each and every one of them is at most 0.4 times m. Why? Because each and every xi is a 0, 1 random variable, and the probability, since we are picking bi uniformly at random from the array, an array has at most 40 a's, the probability of a random element being a is at most 40, 40%, so that's 0.4. So this is the expectation. What about the variance? So because the random variables xi's are independent, the variance is also a sum of variance. And this is 0.4 times 1 minus 0.4, which is 0.6 times m equals 0.4 m. Okay, so now using Markov's inequality, is less than or equal to the expected value of x over 0.6 m. The expected value is 0.4 at most. So over here, notice that m did not okay, this should be, I should write it like this, 0.4. So over here, notice that m did not play any role uh, in this bound. So it doesn't matter how many times you repeat, you will never get more than, the success probability would never be more than 1 over 3. This is the failure probability. So success probability is 1 minus this. And so the success probability would be never be more than 1 over 3, which is the constant. Okay. So now let's see what happens using Chebyshev's inequality. Probability that x minus 0. So Chebyshev's inequality is a probability that absolute value of x minus expected value of x is greater than equals to d is upper bounded by variance over d square. Okay. So over here, okay, let me write it like, yeah. Okay, so I have picked 0.2 over here because what is this? This is And the first one gives us x y greater than equals to 0.6 m, right? So this is what we're interested in, which is the same as this. And there is an or, so this probability can only be larger. So if I upper bound this, I'm done. Okay, so now what's this? This is like, okay, equals to 24 over 20. So that's 1.2 over m. So if the probability is less than or equals to, let's say like some constant over root 10 log n. So using Chebyshev's inequality, we see that we can upper bound the failure probability to be an inverse polynomial. But using Chernoff's inequality, we'll see that you can make this inverse exponential. Because first, let's recall Chernoff bound. So Chernoff bound only works if x is a sum of xi's and each and every xi is an independent 0 1 random variable, which happens to be the case over here. So we can use it, and the bound that we would need, so there are two bounds, but the bound we would need is x. Yeah, delta Eisen's comma 1. Okay, so let's find out the delta over here. So what are we interested in over here? We are interested in x. Yeah, I'm writing this in the form 1 plus delta times expected value. This is upper bounded by delta over here is 1 over 2. So delta square is 1 over 4, and 1 over 4 times 3 is 12. An expected value of x is 0.4 m. So this is what 130. Yeah. Okay, let me just stick to simple. So if m is equal to root n, this is at most a constant, which is much smaller, right? So over here we saw that using Markov's you can upper bound the error probability to be constant. Using Chebyshev, you can upper bound it to be inverse poly, and using Chernoff, you can upper bound this to be inverse exponential. And this is something we observe frequently while trying to analyze the success probability of randomized algorithms. So Chernoff gives you the best results, followed by Chebyshev, followed by Markov. Okay. Now let's look at the second problem. So the second problem is how do we implement the contraction operation in order v size of v time when the graph is given as an adjacency matrix. So we encountered this question while looking at Kargar's algorithm, and the contraction operation was a fundamental operation used in that algorithm. So let's quickly recall the operation, and then we'll see how to implement it in order size of feed time. So we are given an, let's say undirect for simplicity, let's say undirected multi-graph. So what's a multi-graph? Between two vertices, you can have multiple edges, but you cannot have self loops. Okay. So you are given a multi-graph, and what is the contraction operation? So you pick any edge E, and let's say U and V are the two endpoints of that edge E. Then you merge U and V into a combined vertex UV. And let's say there is a W, so that there is an edge from U to W. So now that is replaced by an edge from UV to W. And if there was a W prime, so that there is an edge from V to W prime, then that is replaced by an edge from U to W prime. UV to W prime, right? So it does something like this. So let's say this is U, this is V, this is W, this is W prime, and let's say you have multiple edges going from here to here. And when I contract, I get one vertex UV. All the edges between U and V disappear because self loops are not allowed. And you have yeah, so these two edges become these two edges between U, UV and W instead of U and W. And this edge becomes an edge between UV and W prime. So this is the operation which we are interested in implementing. But the first question over here is, so we know how to give an adjacency matrix for a graph, a simple graph, but how do we give an adjacency matrix for a multi-graph? Okay, so recall that what we do in a simple graph, whenever there is no edge, you put 0. Whenever there is an edge, you put 1. So one way to think of that is this. Every entry counts the number of edges between the two corresponding vertices. And once you think of it like this, there is a natural way to generalize this to multi-graphs. So if there are, let's say, k edges between U and V, then the entries of the matrix UV and VU are 10, are k, okay. So the corresponding, the entry is equal to the number of edges between the two vertices, okay. So let's do that. Okay. So now that we know how to give an adjacency matrix representation, let's look at an algorithm to implement this operation, okay. So let's say I want to contract U and V. So what will we do? We'll do this for all W in phi. So what we'll do is we'll go over the row corresponding to V and the column corresponding to V. Whenever we find an edge between V and W, we would make that an edge between U and W. And so in this process, what we are doing is we are essentially removing the vertex, the row and column corresponding to V, and you would make the row and column corresponding to U to have all the edges that UV would have. So essentially what's happening is that U is becoming UV and V is being deleted. Okay. So if M U comma W, sorry, P comma W is equal to K, okay, is not equals to 0. So there is an edge. Uh, then what we'll do is mu comma w plus it becomes mu comma w plus m v comma w. And recall that we assume that the graph is undirected, so this matrix is symmetric. So we should also do this. Yeah, so these two are the same, these two are the same, these two are the same because the graph is undirected. And at the very end, we should also replace. Yeah, so you also make all of these entries -1. So the entire row, entire column becomes -1. And this denotes that this edge has been deleted. This vertex has been deleted. And since we do not want to process deleted vertices, I should also add this over here. Yeah, because if mv comma w is -1, that means that w has been deleted and I don't need to process that. Okay. So it's easy to see that this algorithm gives you the contraction operation. And the only process we are doing is going over the row and column once. Okay, twice, once over here and once over here to make everything -1. So the running time is order size of. So now let's look at the third question. So we encountered this question while giving a randomized algorithm to check if two matrices are similar. And recall that two matrices are similar. Two matrices A and B are similar. If there exists an invertible matrix D, so that A equals DB times D inverse. Okay. And we gave a randomized algorithm which was doing the following. So it was solving the system of equations AD equals DB. Now this is a homogeneous system of equations, so this always has a trivial solution. And if that is the only solution, then you know that the only matrix D satisfying this is the zero matrix. So there is no invertible D satisfying this equation, and so A and B are not similar. On the other hand, if you have multiple solutions, then you would have free variables and basic variables. So you would write all the basic variables in terms of free variables, and that would give you all the entries of D in terms of free variables, right? Now, what do you want to do? You know that there exists a D satisfying AD equals DB. Its entries are given by like linear combinations of the free variables. And if I put values for the three variables, I get a concrete matrix. So I have infinitely many matrices D, but I'm not interested in a matrix D. I'm interested in an invertible matrix D. So what we want to do is we want to find out if this matrix that we have D, whose entries are like linear combinations of these three variables, if that's invertible or not. And the way we did that was we would put random values for the free variables and check if the determinant is zero or not, right? If the determinant is zero, then we say that with high probability, then we say that, okay, they are not similar. And if the determinant is non-zero, we say they are similar. And the reason this worked is because if they were similar, then there would exist an invertible D that would satisfy this equation. And so the determinant as a polynomial would be non-zero. And so when you plug in random entries, it would be non-zero with high probability because of Schwarzschild lemma. Okay. So over here, we needed randomization to decide whether D was invertible or not. Okay. So so if you wanted to give a deterministic algorithm, here's one thing we can do. Instead of solving AD equals BD, sorry, AD equals DV, let's just solve for this directly. And if we get a D that satisfies this equation, we know that that D is invertible and we are done, right? Okay, so how do you do this? Okay, you have entry, you want to find out D, so the entries of D are variable, but you have entries of D inverse in terms of entries of D, right? So let's say D is Dij, and the entries of D inverse are, let's say, D prime Ij. Then we know that for all I comma j, D prime Ij is the adjoint of, okay, the Ijth adjoint, sorry, Jith adjoint. So the determinant of the thing obtained by removing the jth column, ith row, divided by determinant of A. Sorry, D, yeah, because we are working with D over here. So it's this. And this gives me every entry of Dij as a polynomial in, okay, not a polynomial, a rational function, because the numerator and denominator are both polynomials. So a rational function looks like P over Q. P is a polynomial, Q is a polynomial. So over here, this and this are both polynomials. Yeah, so now that we have d prime ij, why not just plug in d prime ij over here and solve the system? Okay, the issue is the following. So now we know, okay, so when we did AD equals DB, our system of equations was linear, and we know how to efficiently compute a solution of a system of linear equations using Gaussian elimination. But we do not know how to solve a system of rational equations. In fact, we do not even know how to solve a system of polynomial equations when the degree of the polynomials is more than one. So a system of linear equations is a system of polynomial equations where the degree of every polynomial is one. But even if the degree of polynomials was two, we still do not know how to solve the system of equations efficiently. In fact, that problem is known to be NP hard. So that problem is called the quadratic equations or quadratic problem, and that's NP hard. So yeah, so you cannot directly solve for A equals dBT inverse. Okay. So now let's look at another problem. So while looking at polynomial identity testing, we saw this problem. So the problem over here is the following. You have two parties, Alice and Bob, and both of them have bit strings, so string of bits, A and B, and the length of both of these strings are n. And think of n as a large number, let's say a million or 10 million. And what they want to do is they want to check if A and B are the same, and they want to do this by communicating as few bits as possible. And what we want is the deterministic algorithm and a randomized algorithm, which require as few bits as possible. Okay. So now let's look at the deterministic algorithm. So one naive way of doing this is, let's say Alice sends her string to Bob, Bob compares the two strings. If they are the same, Bob returns 1. If they are different, Bob returns 0. Okay, so here's the deterministic algorithm. Else. Yeah, so this is a very simple algorithm. However, what's the communication cost over here? So the communication cost is n bits sent by Alice to Bob and 1 bit sent by Bob to Alice. So n plus 1. It turns out that for deterministic algorithms, you cannot do better than order n. And the reason is simple because let's say Alice or Bob doesn't send even one bit of their string. It's possible that every other bit is the same, that bit is different, right? So if they miss out sending even one bit, that bit might flip the answer. Okay. So with deterministic algorithms, you cannot do better than order n bits, but we would see that using randomized algorithms, you can do much better. So okay, so we want to design an algebraic randomized algorithm, and we saw a strategy to design uh, such an algorithm when we were looking at the polynomial identity testing problem, right? So what was the strategy? The strategy was the following. Uh, you would create two polynomials. Let me call them a tilde and b tilde. And a tilde and b tilde must be the same polynomial if and only if a and b are same as strings, right? Otherwise, they should be different polynomials. Once we have such polynomials, all we need to do is uh, put random values for the variables and then use Schwarzschild to argue that the values of the two polynomials at random points would be the same with high probability if and only if the polynomials are same, right? So let's see how to create those two polynomials. So the polynomials are so let's say that A is the string A0, A1, A2, and so on. So A0 plus A1x plus and it's easy to see that A and B are the same if and only if A tilde equals B tilde. So if A and B are the same, then it's easy to see that A tilde and B tilde are the same because each and every coefficient is the same. On the other hand, if A and B are different, at least one coefficient must be different, and therefore at least one bit must be different. Let's say A2 and B2, then this two coefficients are different, and so these two are different polynomials. Okay, so now all you have to do is pick R from a pick a random R. So the algo becomes this. Uniformly at random from a large enough set, let's say of size n square. Yeah, okay, so this is the algorithm, and I won't argue the uh, correctness probability, but I using Schwarzapple, we have done that multiple times. You can do it on your own, but I'll just write what will happen. So if A equals B, Bob always would always return 1. And if A is not equals to B, Bob sends 1 at least 1 minus 1 over n, capital N. And we get this because the degree of the polynomial is at most n minus 1. So let's say at most n. And Schwarzapple gives us d over size of s, 1 minus d over size of s. Over here, that is n over n square, so 1 over n, this thing. Yeah, you can work this out on your own. It's not difficult. But okay, so now let's analyze the communication complexity. So what does Alice send? Alice sends R. R है okay, to R is a number from 1 to n square, and to send a number less than equals to B for any B, you need at most 2 log B bits, right? Or even like some log B plus 1 bits. So let's say order log B bits. So R requires order log n square, which is order log n bits. Similarly, Bob's answer is just 1 bit. However, the issue R. So question is, how large can A tilde R be? Okay, so it turns out that A tilde R would be huge. Why? Because, okay, let's say, so we pick something uniformly at random from 1 to n square. So with probability 1 minus 1 over n square, it would be greater than 1. So it would be at least 2. And when R is at least 2, just this thing would be, so let's say a n minus 1 is 1. So this thing can be as large as 2 to the n minus 1. And to send 2 to the n minus 1, you would need at least n bits, which is log of 2 to the n minus 1, right? So now we require n plus log n plus 1 bit. So we are actually doing worse than this n plus 1 over here. So this is a bad algorithm. So what's the way to get around this? Well, the way to get around this is that even though I only covered Schwarzschild lemma for rational numbers, it works over any field. And so what we'll do is, over here we are picking the like random numbers from a subset of rationals. Rather, what we'll do is we'll work over a field and pick random numbers from that field. So what we'll do is use Schwarzschild. Okay, work over a finite field FP. So pick a prime P in n square to 2n square. Such a prime always exists. That's known. And work over FP. So recall that FP is the field which contains elements from 0 to p minus 1. The addition is mod p, the multiplication is mod p. Okay. And so now our A tilde is defined to be and B tilde is defined to be and in Schwarzschild we would pick a So you would pick R uniformly at random from the field. And so from Schwarzschild, we would again get these guarantees by using Schwarzschild over FP. Okay, but now what's the communication complexity? So now A tilde R and B tilde R would be in FP. And we know that every element of FP can be at most P minus 1. So let's say at most P. And how many bits do you require to send P? Uh, or an element from 0 to P minus 1? At most order log P, right? And what's order log P? So A tilde R requires order log P bits, which is so P is at most 2n square. So let's say order n square. So this is order log n bits. So total is this order log n plus this order log n plus 1. So that's order log n. Yeah, so by just communicating order log n bits, Alice and Bob can find out whether A and B are same or not with probability at least 1 minus 1 over n, which is good, right? Okay, so this is all I had for today. So let's meet for a regular session from 5 to 6:30 today. Okay, see you.